Or you can't? So are we live? Okay, so I think we're live. So yeah, welcome everyone to this workshop on the Streams library. This will be the first workshop in a series of talks that we will do with the IOTA Evangelist Network. The topic of today will be the new Streams library. And what I will present today is, first of all, the difference between the old MAM library, which is the masked authenticated messaging, and the new Streams. And that will give us a chance to a bit understand where Streams is coming from and what the main difference is between what Streams can do and what we could do previously with MAM. Then we will quickly go and look at the applications of Stream, which will probably clarify a bit why Streams is so interesting and so powerful. Then we will take a look at one application, which is the channels one, and that one will be the one we will be focused on mostly today. Then again, for the channels, we will have a look at how you link messages and what that means. We will then quickly look at the messaging flow so that we all understand in which sequence the different messages need to be published. And then lastly, we will go into the code and we will write up an application which uses the channels to send public and encrypted messages. Okay, so let's start. So the first thing, as said, is a bit the difference between masked authenticated messaging and Streams. So I think we can start by having a look at masked authenticated messaging in the first version, which was published in 2017. And it was available in JavaScript, I think was the first, and then Python, and later Rust. And the goal of this library was basically to provide a solution to send data in an encrypted, unalterable, and authored way. So basically you can send encrypted data. It cannot be changed from when it's sent to when it arrives, and you can verify the origin of the data. And this was done fully on the Tangle. And we had three modes, basically. They were public, private, and restricted, where public just means that you put the data on the Tangle and then you share the address of where the data is stored and everyone will be able to read it. In the private mode, we could encrypt this data, but we only had one encryption key. So once we shared that, everyone who holds the key will be able to read the encrypted data. And then the last one was the restricted mode, and there we had like a separate key. So we could change the encryption key, and then people would no longer be able to read the messages. So this was very useful, and there have been quite a few applications using this, but it had some limitations. And Vlad, in the last IEN talk, Vlad talked a lot about the advantages of Stream. I will not go that deep today because this workshop is more focused on how it's used and how you can write applications today with it. But basically, Streams is the goal of Streams is to provide a framework for cryptographic protocols and application. So what it basically means is that Streams is much wider in scope than MAM. And it's also in some sense an abstraction, and it sits at a level deeper, because with Streams you can build many different applications with many different messaging flows, with different rules and different roles. And you also can use different transport modes. So the Tangle is the one which will be used in the beginning, but you can also do send the messages over IPFS or HTTP and TCP. And also what I think we will probably be most focused on today is the subscriber management. And that's also something that with streams you can do much better than with MAM. So if you have multiple subscribers, you have a much better access to what data is shared with which subscriber. Okay, so let's take a look a bit at how streams is built. So in the last talk by Vlad Semnov from the IOTA Foundation, he went through the entire stack, and he basically showed us all the different modules and what they are and how they're used. So very quickly, we have our core layer, which have the utilities. It has the Troika hash function. It does the random key generation and all of that. Then we have the KEKAK, which is the Spongos transform. We have the Merkle trees and the Winternet signatures. We also have the key encapsulation, which we will use for the session keys. And then we have the message definition language, which is the protobuf 3. But what I think is most interesting for today is that we have a core stack, which are these 6 modules, and then we have an application layer. And the application layer, basically what it gives us is a set of tools and patterns that we can use in order to create these streams application. And as I said before, the channels or masked authenticated messaging is just one application. And it's built using all of this stack. So what is an application? And basically an application is a set of these 4 things. So we have parties, which are like the actors in our application. We have roles, which is basically what the actors do. And then we have message syntax and message semantics. Syntax is just how the message is formatted, and semantics is what the meaning of each message is. And these messages are encoded with the protobuf 3. So what we do when we build an application on top of streams is that we write the program, basically we write the application, and we define all of these parameters. And then we have some wrap and unwrap functions, which basically are things that the parties can do with the messages. So for example, in the channels, and we will have a much deeper look at that later, we at some point need to announce the channel. So what we do is that we create the message inside of the author, actor of the party, the author who sends the messages. We construct the message, we encode it with the protobuf, and then we send it to the Tangle. And that's a bit what this streams application is. So it's a predefined set of messages that you can create and publish onto different transport mediums. And these applications are, let's say, secure by design in some sense, because they are built on top of this cryptographic stack here. So as long as we stay inside the framework defined by IOTA Streams, all the applications that we build will have some set of security guarantees. Okay, so let's take a look at the channels application, which, as I said, is one application of streams. So in channels, which is the, let's say, the new version of MAM, we have 2 parties. We have an author and a subscriber. And these are the roles that they do. So the author, he is the owner of the channel. So he will create the channel. He will also be able to manage the subscribers. So he will choose which subscriber will get access to the channel. He can read messages sent by the subscribers, and we will take a look at the different message types later. He can send signed messages, and he can send tagged messages. Whereas the subscriber, he's an anonymous member, so his public keys are only available to the author. He will be able to verify the messages sent by the author, and he himself will also be able to read tagged messages. And we will look in just a moment at what these tagged and signed messages are and what they mean. But that's just basically the definition of the channels application on Stream. So we define two parties, we define the roles, and then we define the message types. And the message types in the case of channels is we have an announcement message, a change key message, a keyload message, then we have subscribe and unsubscribe, and then we have the signed packet and the tagged packet. And as we have seen before, the streams itself is transport medium agnostic, which basically means that we can send these messages across any type of transport medium. And the tangle will just be one of them. So let's look a bit deeper at the different message types. So the first one we will have a look at is this tagged and signed. So the difference is mainly that tagged messages can be sent by both the author and the subscriber. And it's not possible to identify who the sender is. So these can be published inside of a channel, but they are not signed. So you will not be able to know if it was the author who sent them or if it was a subscriber who sent them. Whereas the signed messages, on the other hand, are signed with the author's keys. And so everyone will be able to verify that they actually originate from the author. And then we have two modes in which these messages can be sent. And they are public and masked. And basically masked just means encrypted. And the public messages are sent to the channel and they will be available to be read by anyone, even people outside of the channel, because you could just monitor the tangle for any new transactions and then you could find one by chance and then you can see the content. And masked means that they are encrypted, and we will see just in the next slide how the encryption is done. But basically, I think what's important here is that we have tagged messages which can be sent by anyone, signed messages which are sent only by the author, and both tagged and signed messages can either be public or encrypted. And that's what these arrows are supposed to indicate. Yeah, and if you have any questions, just leave them in the chat and we will have a look at them after the presentation. So now let's go to the part which is probably a bit more complicated. So we will take a bit more time to go through the next few slides. So this slide is on the concept of linking. So what linking basically means is that you can create a dependency tree between messages. So what we will do as a first thing when we open a new channel is that we will send an announce message. And basically what the announce message does is that it creates the channel and it publishes the author's public encryption key. And that's the NTRU key. And then a subscriber, he will get the location of this message in the tangle. And we will see later in the code how that's done. But basically the subscriber will be able to find this message. And he will then send, take the author's public encryption key, create his own public encryption key, and send the message to the tangle. And it will be linked to this message. So that then you're basically saying, I am sharing this public encryption key for the author who created this channel. And then the author, he will be able to know which subscribers are subscribed to which channel. And so in this case, we use the linking to basically tell everyone to which channel we are subscribing. Then at a later stage, we might share some data. So we might publish some data in a signed message. So the author, he signs the message using his public encryption key, and then he sends the message to the tangle. So now if I receive this message here and I see a signature, I need to verify the signature. So I will need to go back to the announce message and check that the signature from this message matches the signature from the announce message. And that's why we need to link it. Because if I just get this message, I have no reference on which to verify the encryption key. And then all subsequent signed messages, they can be linked to the previous signed message as long as at some point we link back to the announce message. So then for the keyload message, and the keyload message is the one where you basically share the encryption key for the encrypted messages. So what the author actually does is that he collects all the public encryption keys which were sent in the subscribe messages, and he creates a session key for all of them. And then he publishes and signs this session key and sends it to a keyload transaction on the Tangle. So now if the author sends some encrypted data, this can be signed or tagged, whatever, and I want to decrypt the data, I need to go back to one of the keyload messages, get the session key, and then I can use the session key to decrypt the data in the message. And so in this case, this message has a dependency on the keyload message, and the keyload message has a dependency on the announce message. Here because we need the encryption key, and here because we need to check the signature. Now, the cool thing about this is that it allows us to basically have multiple sets of subscribers who have access to different kinds of messages. So in this example, we have a subscriber number 3 who creates his subscribe message and publishes it to the Tangle. And then what the author does is he publishes a second kilo message, but it's linked not to the announce message, but to the subscribe message from the subscriber number 3. And what this basically does is that the session key in this message will be available only to the subscriber. So what we see happens now is that if we link the encrypted data to the first keyload message, all of the subscribers will be able to decrypt it, because all of the subscribers have access to this session key. But if we link the encrypted data to this kilo message, then only the subscriber number 3 will be able to decrypt it, because he's the only one who has access to this session key. Okay, so what this just summarized, it basically means that through this linking, we can do more advanced subscriber management, because we can choose which subscriber has access to which session key. And it also basically tells us that we don't need to link the message directly to the keyload. So as long as down the line we have a keyload, then we can decrypt it, because this is like a dependency tree. So you start here, then you move to the next. Then at some point you find a session key, so you can decrypt all the messages after that. And maybe also to quickly talk about the change key. What the change key does is that it encrypts, so it creates a new public encryption key for the author. Because as we all know, IOTA is currently using the Winternet's one-time signatures, so you only have a limited use of them. After you have used them a certain number of times, you need to change it. And so what you do is that you publish the new keys in a message, and you sign that message with the last key that you previously had. So basically then the subscribers, they can see all the signatures from the previous message. Then you publish the new signing keys, and then after that they will be able to basically use the new keys. I hope this is clear. If not, just put your questions in the chat. So let's now that hopefully we understood a bit how linking works, let's have a look at the actual flow that we have when sending messages using the channels application. So what we see here is the entire flow that you need to go through in order to add a subscriber and share the session key with them. So these are the steps that you will have to do if you want to send encrypted data to a subscriber. So the first thing that you do as the author is that you create a channel. And creating the channel basically just means that you will get one announcement message and the channel address. So the author instance, and we will see later how that looks in code, has basically a method which is called create channel, I think. And it returns you a channel address and an announcement tag. And the announce message. So the announce message is the one which contains the public encryption key of the author. And we publish that to the transport medium, which in our case is the Tangle. But now we need to tell the subscriber where he can find this message on the Tangle. Because if we have a lot of transactions, then obviously it's not so easy to find one specific transaction in the Tangle. So what we do is that we share the tag of the transaction as well as the channel address to the subscriber, so that then he has enough information to find this message on the Tangle. So it's a bit complicated because it's different from how MAM was working. But basically what we do is that we create the message, we send the message to the Tangle, we share the location of the message with the subscriber so that the subscriber can then look up the message on the Tangle and get the data which is written in there. Then the subscriber can take this and update his state. So each of these, they have a state where they store all the information that they need. And when the subscriber gets the public encryption key of the author, he can publish his own one. So we basically do the same thing. We create the message, we publish the message to the Tangle, and we share the location of the message with the author. So that then the author, again, he can go on the Tangle, look for the message, get the data in the message, and add it to his state. So that when the author has the information about the subscriber, he can create the session key. And then we do the same thing again. We generate the message, the keyload message, which is the one which contains the session key. We publish the keyload message to the Tangle, and we share the location to the message with the subscriber. Then the subscriber, he goes on the Tangle, looks for the message, downloads the session key, updates his state, and now they can share encrypted data. And here we see that we have two links, one to the announcement message and one to the subscribe message. And that's because of the thing that I said before, where basically you can either share the session key with all subscribers when you link it to the announce message, or you can share the session key with a single subscriber if you link it to his subscription message. Okay, then the same thing again for changing the signing key for the author. So we generate the message which contains the new signature keys. We sign it, but that all happens internally. We publish the new key to the Tangle, and we share the tag on where to find this message, so that then the author, the subscriber, he can update his state. Okay. Then again, it's basically always pretty much the same thing, also for sending data. So in this case, we want to send some public data. So we create the message, We publish the message to the Tangle. We share the location of where the message is on the Tangle, so that then the subscriber can read the message. So he finds the message and he can read it. Same thing for the masked message. We create the message, we send it to the Tangle, we share the location, the subscriber finds the message, he can decrypt it, and then he has access to the data. Yes, I think that's it. So I guess that's where the main difference is to MAM, because in MAM we didn't have to share the location of the message, because what we would do is that we would share the first location of the first message, and then the subscriber, he could dynamically basically derive all future locations of the coming messages. And at the moment, we cannot do that in Streams. There is an issue on the Streams GitHub, which basically proposes or basically asks for that to be available, but right now it's not. And the implication of that is that every time we send a message to the Tangle, we need to explicitly share the location of that message, so that then the other party can find it. Okay, so I think we can go over the code. The code is already available on GitHub together with the slides. So if you're looking at this on YouTube or you don't have access to the slides, you can go on this GitHub link, and there you will find the entire slide deck. So let's get to the code. So as you might know, the Streams library is available in Rust right now. There are different reasons why they're using Rust. I personally like it a lot. I think it's very cool to program with. But for those of you who are not too familiar with the language, basically what we have is a cargo.toml file, which is the package.json correspondence. So here we have our dependencies. And in this case, we have obviously the IOTA Streams as a dependency, as well as the IOTA library, the client library for Rust. And then we have the standard failure package, which is I think needed for any kind of Rust application. So given that it's a lot of code, I have written it already, and now we'll just basically make it appear like this. So it will probably be pretty fast, and you might not be able to code like in real time following what I'm doing. But as I said, the code is on GitHub, so you can have a look at that. So the first thing that we will do is to basically add all of our dependencies. So here we have the IOTA client, and then we have all of the stream dependencies. So we have the transport mediums, we have the send options, we have author and subscriber instance, we have a message type, and then we have the utility stuff, so like tries and ternary bits. We will do all of the coding inside the main function, so that's not something you would usually do. But what I will do now is to basically show this flow here. Let me go back. This flow here. So we will do all of this. We will create a channel. We will add a subscriber, and then we will share the session key. And then we will send a public message and an encrypted message. So we will do all of that in the main function. So the first thing that we need to do is to connect to the IOTA network. We will do that to the DevNet. I know that the community network is more up to date, but for some reason, all of the things around streams are still run on the DevNet, so I decided to keep it with that. So then we need to define the sending options, and these are like network specific. So in this case, we have the weight magnitude, which in case of the DevNet is 9. and then we will set the proof of work to be done remotely on the node. So now we can start to basically build our channels. So we will create the author. We do that by calling the new function, and it takes 3 parameters. So this is the seed. This is the amount of signature keys that we will be able to use. So this is 2 to the power of 3 keys. So we will be able to sign 8 messages from the author. After 8 messages, we need to do the key change, which is what I showed before in the slides. And the last parameter is whether or not we need to have the NTRU keys. So this basically just means if we want or not to send encrypted messages. And in this case, we want. So I will keep it at true. Okay, so now that we have our author instance created, we can create the message and we can create the channel. And we do that by calling author.announce. And this will return the announcement message. And the announcement message is this one. So by calling author.announce, it will generate this message here. So that's the one that we will send to the Tangle. But before we do that, we will store the tag, which is basically the thing here. This is the thing that we will have to share with the subscriber so that he can find the message then. So basically we have the message. Then from the message, we do .link.messageID, which is the tag. And then we transform it to a string. And then we print the tag. So now that we have done that, we can send this message here to the Tangle. And we do that by connecting to the client and calling send messages with options. We give in the message that we want to send and the options that we defined up here. And then for those of you who don't know Rust, basically we sometimes have this unwrap, which basically just means if there is an error, throw the error, so basically crash the code. And if there's no error, return me the value. So it's like a try-catch in some sense. Then we will wait for 20 seconds so that the message has time to get to the Tangle. And then we can create the subscriber. So similar to before, we do a subscriber new, we put in a seed, and we have again the availability of the NTRU keys, and we set it to true because we want to read encrypted messages. Then we get the channel address from the author. So here we can do author.channeladdress and transform it to a string. And the reason why we need that is because now we can use the tag from the message that we sent to the Tangle, combine it with the channel address, and this will give us a link. And the link is basically the location of the message on the Tangle. So this is this. So we got the channel address and the tag from the author. We use it to create the link. And then we use the link to find the message. So let's do that. We have the link. Then we connect to the client and we call receive messages with option and we give it the link. And then these are the receive option, which in this case we can leave empty. So what we do by doing this is basically we tell the client, go look at this location and return me the message which is stored there. So we will basically get the announcement message from this. And then now this will return a list and we will take the first element of the list. And now basically we got this announcement message and we read it from the Tangle. Now what we need to do before we can actually use it is that we need to parse it. So we can do response.parseHeader. Then we check whether it is an announcement message. Because given that you can link different messages to the announced message, if you send a lot of messages at some point, you might also have keyload messages here or other kind of messages. So basically you need to check that what you get is actually an announced message. And this ensure here just means if it is an announced message, then okay. If not, you throw an error. So now that we know that the message is actually an announced message, we can do subscriber.unwrap announcement. And this basically updates the state of the subscriber with the author's public encryption key. So just to quickly recap, what we did is that we created the message, we sent the message to the Tangle here, then we shared the location of the message using the tag. The subscriber then reads the message from the Tangle, checks that it's actually an announced message, and if it is an announced message, he can update his state and store the public encryption key of the author. So at this point, the subscriber has the encryption key of the author, which means that he will be able to verify signatures with it. So at this stage, we can already start to send signed messages. So the author can send a public message, sign it, and the subscriber will be able to verify that the signature is correct. But we want to send encrypted messages. So what we have to do now is this. So now we are at this step. What we need to do now is to create the subscription message, which contains the public key of the subscriber. Then the author needs to receive that, add it to his own state, and then he can share the session key with which we can encrypt the messages. So let's do that. What we will do is similar to before. We will generate a new message, and we can do that by calling subscriber.subscribe and give the announcement link as a parameter. And this is because we need to link the subscription message to the announcement message. So we put the link, which, as I said before, is the location of the announcement message. We give it as a parameter. Now, same thing as before, we store the tag because we need to share it. And then we can send the subscription message to the Tangle. And we do that as before, client.send message with options. So now, at this point in the program, we send the subscription message to the Tangle and we store the location of it. So now we need to wait some time so that the message can propagate in the network. Then we can generate the link of where the message is stored. And we do that again with the channel address and the tag. Then the author, he can again call client receive messages with options. And so basically here you can read the subscribe message that we published up here. We again take the first message, the first response in the list, and we print the tag so that then later we can go in the log and see that the tags match. Then similar to before, we parse the response. We verify that it is a subscribe message. And if it is, we can call author.unwrap subscribe, which basically updates the state of the author and stores the subscriber's public encryption key. So now we are here. The subscriber published his message, he shared the tag, the author finds the message on the Tangle, and he updates his state. So now the missing part is share the keyload. So that's what we will do next. To do that, we can call author.share keyload with everyone, and we link it to the announcement message. So again, we do this link up here. So we share it with all the subscribers of which we have the public encryption key, which in this case is just one. Again, we get the tag from the message, and then we send the message to the tangle with the send options as before. So now the session key is on the tangle, and the subscriber needs to download the session key, update his state so that he will be able to read the encrypted messages. So we wait 20 seconds for propagation. Then we generate the link using the tag that we just got. And then we can call receive messages with option. So we download the message from the tangle. Again, we take the first one. We parse the message. We check that it's a keyload. And then we call subscriber.unwrap keyload, which takes the message and updates the state. And at this point, the subscriber in his state has the session key, which comes from the keyload. So he will be able to decrypt any encrypted messages sent by the author. So that's what we'll do now. We will send some public messages first. So we will create a public payload variable, which will be made up of tries. We will generate the tries from the ternary bits, and we will generate those from a string. The masked payload will be empty, because what we will do now is send a public message first. So to basically sign the message, we can do author.signPacket. We put in the announcement link, which basically means that we will link this message to the announcement message. And we will put in the public payload and the empty encrypted payload. Then we will get the tag to this message. And then we will send the message to the tangle. Then we will do the same thing for a masked message. So in this case, we will leave the public payload empty. Now we can also put a public payload here. So then you will basically have a message of which you can read a part, but not all of it. And we will write some masked data in here. Then again, we will sign the package, but this time we will link it to the keyload. And the reason we do that is because the keyload message on the tangle has the session key. And then we put in the public and the mask payload just as before. We store the tag, and that's it. Now we need to send them. So here we can do again, send message with option. We put in the masked message that we just created, and then it gets sent to the tangle. Then we wait 20 seconds so that the messages can arrive. And now we do the same thing that we have been doing all day long, is that we take the tag, we combine it with the channel address to get the link. Then we will use the link to look in the tangle for new messages. So here we have the link to the public message. So the subscriber will receive the public message. Again, we will parse the message, check that it's a signed message. And then we can call unwrap signed packet. We put in the parsed message, and it will return the two payloads, the public one and the private one. And then we can print the public payload. And the signature is actually checked at this stage. So when we call unwrap signed packet, the subscriber will check that the signature he has in his state from when he called unwrap announcement, which is here, is actually the same one which was used to sign this package. So if we try to call signed packet before we unwrapped the announcement message, then it will basically give us an error and say that the signature is not valid. So we will do the same thing for the masked message. We will take the tag, combine it with the address, generate the link, and then we will read all the messages stored at that link. And we will parse it, check that it's a signed message, and then we can call again unwrapped signed packet. So you can see that it's exactly the same method that we use. But in this case, we will not only read the public payload, but we will also try to read the masked payload. And given that in the state of the subscriber, we have the session key, and we got that from doing unwrap keyload, now we can basically decrypt the masked payload. And so we will get access to the data. So that's it. I think that's all of the code that we will have today. Now to run code in Rust, you do cargo run. Now hopefully the connection, oops. Something happened, not found in the scope. So that means that we don't have the dependency. What is that? Okay. Let's see. Oh, okay, I don't know what happened there. But basically, if you're not familiar with Rust, the compiler is pretty strict. Basically, every time you do something that you're not supposed to do, the compiler will throw an error and usually be pretty specific with what the problem is. So now here it looks like it didn't find the dependency. Okay, but let's have a look at what's happening. So we started the program and it ran the first piece. So we announced the message and we generated this message with this tag here. Now what it will do next is, oops, that's a connection error. Yeah, I hope we can at least one time get through the entire process without the connection dropping. I'm not sure if this is a problem with the DevNet node or with my network, but I get this error here, the specific error, quite a lot. So yeah, I hope it works at least one time. So yeah, now we generated the message with the tag. We sent the message to the Tangle. So we are at this point here. Now it's waiting 20 seconds in order for the message to propagate. Yeah, it will take some time. And the reason we need to do it is because if we don't wait that the message has arrived to the Tangle, then the subscriber, he will not be able to find it. So here we see subscriber announcement message found at this tag. So that's good. Then he unwrapped the message. So now we are here. So we received the message from the Tangle, we unwrapped it, we stored the signature keys from the author. Then we generated the subscribe message. So now we are here and we send it to the Tangle. Then the author, he received the message. He shared the keyload and he sent the keyload to the Tangle. So now again, the subscriber will be able to use this tag to find the keyload message on the Tangle. He will be able to unwrap it, to store the session key in his state. And then later, he will be able to read the encrypted messages. So here we signed the message. Now it will send it to the Tangle. Yeah, there it is, send it to the Tangle. Then the encrypted message also generated and sent to the Tangle. Yeah, so now the subscriber should be able to receive them and to read these two messages here. I'm public and I'm hidden. So let's wait until that happens. So here we go. The subscriber found the messages with this tag. He unwrapped it and he found the public message, I'm public. And then he was also able to find the encrypted message and to decrypt it. And he found I'm hidden. So that's pretty much it. As I said, the code is on GitHub. You can download it and run it yourself and play a bit with it. Yeah. So I guess we have 10 minutes left to take some questions. Now I will stop to share my screen and we'll see if there are some messages, some questions to answer.
Okay, Alessandro, that was very, very good. I'm sure it's going to be of much help for guys trying to develop stuff. So guys, if you wanna question.
Okay, yeah. Mike Bennett, you said earlier that streams cannot run only on the Tangle, but anywhere. The slide 8 description is very specific to the Tangle. Yes. So the way it works is that the transfer medium needs to implement a certain interface. And Vlad, as I said, I don't know exactly what the interface is, but you can have a look at the talk that Vlad gave on the IEN. And there he went into the specifics of what interface needs to be implemented by the transfer medium. But yes, the slides are very specific to the Tangle because the channel application, which was released now, it was like developed with the Tangle in mind. Now, I have never tried it with another transfer medium, and I also haven't seen any examples using another transfer medium. So I guess we will have to wait and see how that can be done. I guess we might need to have some like wrapper if we want to use like IPFS, for example. So that's not available yet, but we'll see what the foundation comes up with. I hope that answered the question. Okay, is Stream working on Comnet? It is supposedly. It never worked for me, and I can, because basically what happens is that if you connect to the Comnet, you will get an error which says something like command not found or something. And from what I heard, that is because you're connected to a node balancer. So the node I was connecting to on the Comnet was the one from the Tangle, so the tangle.org, and that has a node balancer. So I think there's some issue with connecting to a node which is behind a node balancer. But yeah, I think you should try it. The channel slide library that is on the IOTA community repo, which I'm developing together with Reloy, who is another great developer interested in streams. So in that one, we just implemented the option to connect to the different networks. But honestly, I haven't tried it yet. So I hope it works, but I cannot guarantee. Yeah. Okay. So I guess we don't have any other questions at the moment. So yeah, I think we are done for today. If you have any more questions, you can reach out to me on the Discord. You can find me at AleB, and have a look at the slides. In the last slide, there's some reference to the different documentations, both for Rust and for the IOTA streams, as well as the link to the channel slide library I was talking about before. So I guess that are great resources to get started as well. Yeah, so thank you very much for everyone for joining, and good luck with using streams.